And we're back. And you're probably wondering, what's up with this? You know what? I figured it'd be kind of different and interesting to go and wear this helmet. This is a British World War II era helmet, and it's the genuine article, it's the genuine thing. I want to point out to you guys that the helmets, they were originally designed not to be bulletproof. That wasn't the idea behind it. But when artillery would land, explode, and pieces of metal would be flying everywhere, this was supposed to protect this. That's the idea. And that was the idea behind it. Okay? And if you look at some of the old World War I photos, you might see some of them have the helmet back like this. And it wasn't because they were being arrogant. Okay? The reason why they were doing that was to protect back of the head and the back of the neck from possible shrapnel. Okay, now you got your history lesson. We're going to go on and get into chapter 18, section 5. We've got to talk about the human impact of air pollution, because air pollution contributes to things like asthma, chronic bronchitis, emphysema, lung cancer, heart attack, and stroke. Ooh. Go figure that. So, what happens? Why? What's going on here? So, what are the health effects of air pollution? Well, remember, the human body, God designed it that there would be natural defenses, that they can fight against pollution. Because, as you know earlier in the chapter, that trees, bushes, plants, grass, they will give off some pollutants out there. And that's a natural thing that happens. Okay? And like the human body's natural defenses can fight it, there is such a thing as there's too much and it's overwhelmed and people get sick. So, first off, we got to look at lungs. How is it that you have a defense in your lungs? So, there's tiny little hairs called cilia. Okay? There's tiny little hairs called cilia, and they wave back and forth to clean your lungs of the particles. Okay, I whip my hair back and forth, I whip my hair back and forth. Okay, so that cleans out the particles out of your lungs. This is where you start running into problems for people who smoke cigarettes, because there's the tar that is in the tobacco that settles in on these hairs. And eventually, what happens is, instead of being like this is what it should be, you start adding up, and now they're not moving, and there's more and more, to the point that you don't have any anymore. And that really means bad things for the owner of the lungs. But there's also other things besides tar that would get in from smoking tobacco. Fine and ultrafine particles also get into the lungs. Now, this stuff can also cause things like lung cancer, heart attack, stroke, emphysema. Well, wait a minute. How could it consider, a heart attack? Well, remember, some of those particles, if they're so tiny, I mean, could actually get into your bloodstream. Okay. So the reality is, when you look at the Environmental Protection Agency, their estimates are anywhere between 150,000 to 350,000 people die each year from indoor/outdoor pollution. Wow, that's a lot. Yeah, exactly. So, air pollution is certainly a consideration, and yet it is a natural part here of living in Southern California. I can tell you, growing up here was not great for air pollution. Okay, I could tell you of days there was so much smog in the air, you were crying. I was crying, and it wasn't because I was happy, and it wasn't because I got beaten up. I was crying because the smog was so bad, my eyes were watering. Okay, it was awful. I could tell you of the days in high school we did not go out to PE because we had smog alerts. And if we ran around like we normally would in PE, what would that do to our lungs, for crying out loud? So a lot of excitement for PE was we got dressed and we got to sit at the picnic tables. Wow, that was fun. Yup. Yeah. The 70s and early 80s in LA was not a fun thing. And this thing doesn't want to cooperate. So, of course, there are other things going on out there. There's legal, economic, technological tools that can help clean up air pollution. But that's kind of after the fact. It takes more effort to clean up the spill, to clean up the mess after it's made. How about preventing the mess? How about preventing the pollution? That might be a good problem for us. You gotta be kidding me. Every time I put on a new YouTube video for you guys or engineering or chemistry, I get this guy who comes up and he makes these very generic comments like, nice video. It was really good. No, 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 no. Oh, no, no, no. We are not doing that. No, no, no. We're going back in here. Okay. So we have looked at, we've looked at indoor air pollutants. We've looked at what kind of an impact does air pollution have on the human body. Okay. Now let's look at the legal stuff. We've talked about that. We do have laws and regulations that can reduce air pollution. We have the U.S. Clean Air Acts that have passed in 1970, 1977, and 1990. Now, of course, the thing is, well, what's the difference between 70, 77, and 90? Why do we need to pass these? That's because there's other kinds of pollutants that other kinds, let me rephrase that. There are other things that now are considered pollutants in 1990, but they were not in 1970. Okay, it's kind of like adding new bad things. Okay, excuse me. So, establishing air pollution regulations that the states and the major cities would be taken care of for this. Okay. Now, because of that, you have what's called the NAAQS, the National Ambient Air Quality Standards. Okay, there are 6 major pollutants that they're focusing on: carbon monoxide, nitrogen oxides, sulfur dioxide, ozone, lead, and suspended particulate matter. Those are the big ones. Now, you got to ask yourself, hey, what are the sources of these? Well, you could think of car exhausts. You could think of burning coal. Burning coal, oh man, you got plenty of SO2 put out there, the sulfur dioxide, mercury, radioactive isotopes. But here, when we're looking at the amount that's going into the air, that's why they're focusing on these particular pollutants like CO, NOx, sulfur dioxide, SO2, ozone, O3, lead, PB, and suspended particulate matter. Yeah, exactly. Now, the EPA has also set up hazardous air pollutants, or HAPs. Okay? Chlorinated hydrocarbons, volatile organic compounds, toxic metals. Ugh, what? Chlorinated hydrocarbons. What are you talking about? Hydrocarbons, they have carbon and hydrogen. Now, add a chlorine to it. It becomes chlorinated hydrocarbons. Volatile organic compounds, we've talked about that earlier in the chapter. Toxic metals, lead, mercury, cadmium. Oh gosh, copper is another one. So there are all these different metals that are toxic depending on how much you have. But mercury is like one of the worst ones. Cadmium is a really bad one too. Okay. Lead is another one. Now, we have what's called a TRI, the Toxic Release Inventory. Now, that's a law requiring companies to report their waste, their releases, and waste management of 667 toxic chemicals. So, this is a way of keeping an eye on what pollutants are actually being let go. How are we managing it? Okay. And in this case here, we are assuming that the companies are going to be honest about it. Okay. And that certainly would be a big issue. And I'm going to finish off the chapter here as I go into 18.7 with you guys. Okay. So let's talk about the ozone. Let's focus on the ozone layer here. We know that there's been a number of chemicals that have reduced the ozone layers, the levels in the stratosphere. Now remember, that's way up there, and allowed more harmful UV radiation to reach the Earth's surface. Now, have we actually been able to reverse the damage? Good news is, yes, we have. We can reverse the ozone depletion by stopping production of ozone reducing chemicals and adhere, meaning follow, obey, to international treaties banning the production of these chemicals. So we talked about what was the ozone that does. It cuts out the UV radiation in the stratosphere by 95%. Okay. Because if you ever notice, if you go to the beach, and even if it's a cloudy day, if you don't put the sunscreen or you don't wear a shirt, things like that, you can still get sunburn. Well, what's causing the sunburn? Is it the visible part of the sun's rays that's doing the damage? No, it's not. What's actually doing the damage is ultraviolet radiation. Now, you guys are more familiar with it when you see the black light. That's the closest our eyes can see the UV radiation, because our eyes don't make it out. So the closest we get is that violet color, okay, that you find on those black lights. So what's the story with all of this? In 1984, there was a concern in the Antarctic. About 40 to 50%, okay, in some places 100%, it went away. What happened? Well, the ozone layer got so thin it wore out. It went away, and you literally had an ozone hole over the Antarctic. Okay, so what did that mean? Well, that meant that the sun's radiation was unfiltered practically, hitting the ground, especially the ultraviolet radiation. Now, that was September, October of 1984. Okay, in February through June, okay, it was 11 to 38% ozone loss over the Arctic. Okay, so that's when you run into the ozone hole. Now, has that hole widened? Has that hole closed over time? Yes. Yes, it has. But still, we need to be responsible about that, and we need to stop producing those chemicals that actually react with the ozone layer. Okay? Because that is a protection that God put in there, otherwise, we would be dead. Okay. Now, how in the world did we understand about the ozone layer? What's going on? Well, remember, you got it happening there over the South Pole, the Antarctic. But you had places like certain places in South America and Australia, the ozone was thinning there too. And it turned out, how did we know this? What told the scientists, hey, there's a problem with the atmosphere here? The number of cases of skin cancer reported, it went up a lot. Okay, skin cancer is no laughing matter. It really is not. Okay, it can kill you. So that's what tipped off the scientists to start looking at the sky and start analyzing what's going on with the ozone layer. And that's when we found out. Now, where we are, the ozone layer wasn't really affected. We were okay. But if you're looking on the south side of the planet, when you're looking at places like Australia and certain parts of South America, okay, New Zealand, and the Antarctic, oh, that's where the problem came in. So that's where you get the ozone hole. Okay, so here's a picture of the ozone hole right here. Here is your southern part of the hemisphere. There's the Antarctic right there. And this is the hole. You're sitting there going, oh my Lady Gaga, it was that big? Yeah, it was that big. Now that hole does become smaller. It does get bigger, so it kind of opens and closes. And that's what we've been living with since then. But since we've stopped doing a lot of those chemicals, making chemicals that react with the ozone in the atmosphere. That, ladies and gentlemen, has made a huge difference for us. So let's take a look here. All right. So what's happening here in this thing besides Darth Vader there? So we're showing what's happening with the process of the ozone and how it ends up getting the, what's the process here. So what happens if you look at number one, it says oxygen molecules are photolyzed. In other words, yielding two oxygen atoms. This is a slow process. So in other words, O2, because of the sun's radiation, breaks off into two individual oxygen atoms. Now, what happens is you look at step two. Look over here. Ozone and oxygen atoms are continuously being interconverted as solar UV breaks the ozone and the oxygen atom reacts with another oxygen molecule. It's fast. So what's happening is the O2 combines with that lone oxygen you got from here to form this particular thing. Okay, to form this O3. All right. And then what happens is this interconversion process converts UV radiation into thermal energy, heating the atmosphere. So that's really what it is. This is the natural process that you're seeing there for O3. And what does it do? So you got start out with O2, breaks off into two separate atoms, right? Then you've got other O2 that join up with the UV radiation. It makes it possible. It absorbs that, and you now have an O3. Okay, and that's what's happening with the O3. It kind of goes back. It kind of goes into a loop there. Okay. All right, ladies and gentlemen. So this is actually the end of chapter 18. Okay. And I'm going to sign off for that, and I will catch you guys at a later time. Because remember, I'm speaking to the future. You're listening to the past in your present.